Hello everyone, welcome to this video on bagging and random forest. Bagging is also called bootstrap aggregation. It is a generic technique for improving the robustness and stability of a machine learning model. Bagging reduces the variance of the model and helps to avoid overfitting. Bagging runs the following steps. Given a training set D of size n, bagging generates M training sets from D1 to Dm, and each of them has L observations, which are sampled from D uniformly and with replacement. Usually L is set as n. Bagging then trains M classifiers by executing the same machine learning algorithms, such as decision tree algorithm on the above obtained M training sets independently. Predictions of all these M classifiers on new coming data are averaged as final outputs. Note some observations may appear multiple times in one set because of selection with replacement. Fraction of unique observations in each set is 0.632 if n is equal to L. This is because the probability of an observation not being selected with replacement in each round is 1 minus 1 over n. So the probability of an observation not being selected in n rounds is 1 minus 1 over n raised to the n. Fraction of unique observation equals 1 minus 1 minus 1 over n raised to the n equals 1 minus e raised to the negative 1 equals 0.632. Bagging decreases the variance of the model and helps to avoid overfitting. It reduces testing error of a base model by the factor of 1 over m if trained models are uncorrelated. However, trained models are always correlated, which limits the advantage of bagging. In addition, decision tree is a greedy algorithm. It results in many trained decision trees with the same structure and are highly correlated, even though they are trained on different sets. Random forest is an improved bagging of decision trees. Like bagging, M training sets are generated by sampling from original set uniformly and with replacement. Then M classifiers are obtained by running the decision tree training algorithm on all above training sets independently, and predictions of all these M classifiers are averaged as the final output. However, random forest has a different way of determining which feature will be selected and used for splitting nodes and growing the decision tree. In bagging of decision trees, all features will be evaluated for splitting any nodes during training any decision trees, while in random forest, only a subset of randomly selected features will be considered for splitting nodes. This constrained selection in random forest will help to reduce correlations among trained decision trees, thus improve accuracy of bagging and lead to better bagging of decision trees. In random forest, there are some hyperparameters. Those are ensemble size and number of features used for splitting nodes. Ensemble size is the number of trained decision trees in bagging. Usually a larger ensemble size always means a better bagging of decision trees. The other hyperparameter is the number of features used for splitting nodes. Unlike ensemble size, hyperparameter number of features p to the s used for splitting nodes is hard to tune. Basically, neither a large value of p to the s nor a small value of p to the s is good. This is because a large value of p to the s will increase correlation among trained decision trees, while a small value of p raised to the s will increase bias of individual trained decision tree. Relationship between p to the s and overfitting or underfitting of random forest is summarized as follows. If p to the s is too large, all trained decision trees are highly correlated. Like single decision tree without bagging, random forest might overfit training data. However, if p to the s is too small, individual trained decision tree has a very high bias. Bagging of classifiers with high bias might still underfit training data. For classification, the default value of p raised to the s equals to square root of total number of features. For regression, the default value of p raised to the s is total number of features over 3. We can also adopt hyperparameter tuning techniques, such as grid search or random search, which will help us find a good value of p raised to the s automatically. Commonly used hyperparameter tuning techniques split all labeled observations into training and validation set. Then train a decision tree with a candidate hyperparameter setting on training set, and measure the quality of the candidate hyperparameter setting by the accuracy of the trained decision tree on validation set. In random forest, there are some observations which are not included in the training set because of sampling with replacement. All these observations are called as out-of-bag observations. We can estimate testing error of random forest by its error on out-of-bag observations. So hyperparameter tuning techniques does not need to split all labeled observations into training and validation sets. Besides classification, random forest can also be used for finding important features or ranking features based on their importances. Given a feature, we can sum all purity gains of nodes in which the given feature is used for splitting, and consider this value as a measure for feature importance. Bagging or random forest can be understood from bias-variance trade-off point of view. We know that squared testing error can be decomposed as the sum of squared bias and variance of a model. In theory, bagging or random forest is understood as an effective approach to decreasing the variance of single decision tree model. But in practice, people observe that bagging or random forest also slightly decreases bias of single decision tree model. Thank you for joining us.